Hi everyone, my name is Thomas Kim. Today is September 19th, 2020. This is my third episode about vector calculus and classical electromagnetism. In this episode, I will discuss how to derive mechanical vibration or mechanical wave equation. We will learn something about mechanical wave and wave functions. Then using Maxwell's equations, we will eventually derive the speed of light. In the next few sessions, I will also explain how to solve partial differential equations. I actually learned how to derive mechanical wave equations back in 1980s while I was in high school. My physics teacher taught us how to derive these wave equations, though he didn't explain how to solve partial differential equations. I personally believe Korean education system is one of the best of the best in the world. Being born as a South Korean is a blessing. Which country in the world does provide as good educational videos as does South Korean EVS? For example, if I click one video, he is explaining about uncertainty principle. For example, if I click Schrödinger equation, he is now explaining about Schrödinger equation. Tens of thousands high-quality videos by the best teachers in South Korea are provided to all South Koreans. Even that, it is absolutely free. Take full advantage of EVS free educations. Without further ado, let's get started. I will close it. This is our wall, and this is a string. This string is tight. This is fixed. And this is length of the string. And we apply a force. This is F. The mass of this string is M. The mass of this string is M. Its length is L. So its density is called linear density equals M over L. Now in this segment, we denote horizontal axis X, vertical axis Y. So here X, this point, X plus delta X. We assume the density is constant. So we can say delta X is this length, segment length. Its mass, segment mass. From this equation, we can say ms, segment mass, equals delta x rho. This is our equation 1. In high school, we learned the definition of derivative. This is vertical axis and this is horizontal axis. This is our function. X is here and x plus delta x is here. So this point is fx and this point is fx plus delta x. This is x-axis, this is y-axis, this is graph for f of x. We create a segment passing 2 points. This is delta x, this is delta y, or fx plus delta x minus fx. So delta y over delta x equals delta x over delta y. This angle is theta, so tangent theta. If we take limit delta x approaches 0, then this is dy over dx. This is definition of derivative. This is our equation 2. In high school, we also learned something called mean value theorem. Mean value theorem plays very important role. The mean value theorem says that f(x plus delta x minus f of x over delta x equals df x bar over dx, where x bar is greater than x, less than x plus delta x. The mean value theorem tells us that there exists x bar between x and x plus delta x. This is called mean value theorem. This is our equation 3. Because we said linear density law is constant, x bar is the center of the segment delta x. Now we will stretch this string upward like this. This is our wall. This is horizontal axis. I will denote phi x. Vertical axis phi y. This is L. This is 0. Our string is stretched like this. It is exaggerated. X is here. X plus delta x is here. So I will create a tangent line T and a tangent line T. This is a horizontal line passing through this point. Also horizontal line passing through this point. This angle is theta plus delta theta. This angle is theta. This T is tension. X plus delta x T. This T is T x T. I will delete this part. This is x. Our x bar is here. X bar. When a vector t is given xt, this is horizontal line passing through this point. This angle is theta. When a vector t, x plus delta x, t, this is horizontal line. This angle is theta plus delta theta. This t is this t. This t is this t. Now we will split this t tension and this t tension at point x here and at point x plus delta x here into horizontal and vertical component like this. This is vertical component. This is horizontal component of t. I will denote h xt vertical component v xt. In the same manner, this is horizontal component of this t, h, x plus delta x, t. This is vertical component of t, v, x plus delta x, t. Then v, x, t equals t sine theta. T x t sine theta, this angle. Then horizontal component t cosine theta. horizontal component t xt cosine theta. Now we divide term by term like this. Then v over h equals t cancels out sine theta over cosine theta equals tangent theta. So v equals h tangent theta. This is our equation 4. Please remember equation 1 and equation 2 and mean value theorem, equation 3 and equation 4. We will use these equations shortly. Now I will scroll up. Newton's second law of motion says that when a body is under the influence of external forces, the body experiences motion. So this is our segment of this string. T, x, t, and t, x plus delta x, t. This segment of our string experience motion. Sigma Fi equals ma with acceleration a, where m is the mass of this segment. Please observe that this segment moves up or down, but it does not move horizontally. This segment does not move horizontally. That means hxt is constant. Also, sum of horizontal components of t is 0 because this segment does not move horizontally. For example, the sum of t horizontal component equals, this is increasing x direction, so h x plus delta x plus t, this term is positive. This horizontal component directs to the increasing x direction. In this case, horizontal components points to decreasing x direction, so it is negative, minus hxt. This is sum of horizontal component. Because horizontal component h is constant, this and this are same in magnitude, so it is 0. Now let's think about vertical components of tension T and T. Sum of vertical component of T equals, in this case, V is increasing y direction, so it is positive. V x plus delta x t, this term is positive. In this case, Vxt, it is pointing to decreasing y direction. So negative Vxt. This is the net force exerting on this segment. This segment's mass is ms, equals ms times now acceleration. This acceleration, this segment moves up or down, or vibrates up and down. So this is y-axis, so it should be d square y over dt square. At point x equals x bar, okay? Because this x bar is somewhere between x and x plus delta x here. Now I scroll up, ms, the mass of this segment is delta x rho. So I scroll down, equals rho delta x d square y dt square. Now we divide delta x like this. V x plus delta x t minus v x t over delta x. I will scroll down. Then if we take limit delta x approaches 0, v x plus delta x t minus v x t over delta x equals rho d square y over dt square. Here x equals x bar. If we take limit, it is round v over round x equals this term, is this part, rho d square y over dt square. From this equation, v equals h tangent theta. We substitute this equation here like this. Round over round x in place of v, h tangent theta equals, if we scroll up, tangent theta equals dy over dx. I scroll down, so it becomes round x h round y over round x equals this equation is this equation. So we write this part, rho d square y over dt square. Please note that horizontal component h is constant, so we can factor out h like this. H round over round x round y round x equals rho d square y over dt square. Or we can say h round square y over round x square equals rho d square y over dt square. We now solve this equation with respect to this term like this. D square y over dt square equals, we divide rho, so it becomes h over rho round square y over round x square. Now let c root h over p. Then we can write d square y over dt square equals c square round square y over round x square, where c equals h over rho. So this is one-dimensional string vibration wave equation. In this configuration, if we scroll up, y is the axis of the vibration of the string. Instead of y, we can expand this equation for three-dimensional vibration like this. We will substitute P for Y. Then if we rewrite d square P over dt square equals c square parenthesis round square phi over round x square plus round square phi over round y square plus round square phi over round z square. We sometimes also write equals c square del square phi, where del square is Laplacian operator round square over round x square plus round square over round y square plus round square over round z square. This is called Laplacian operator. So this is our three-dimensional wave equation. If we solve this equation, then we can understand the meaning of C.